Hi everyone. Today we're going to be going over EE471, the midterm review, and so we will get started. So what we're first going to focus on basically is performance, stability, and steady state error. And so we're going to look at each of these in depth. So remember that a complex number S can be represented by a real part sigma plus an imaginary part omega. And so you can also represent a complex number in polar form, so with a magnitude and the phase angle. And so you need to know how to convert between these two types. And so if we're looking at the polar form, m is equal to the square root of sigma squared plus omega squared. And then theta is equal to tan inverse omega over sigma. And so it's the imaginary part over the real part. And then if we have to calculate sigma, sigma is equal to m cosine of theta, and omega is equal to m sine of theta. And so this would be from rectangular to polar form. So rectangular to polar form. And this would be from polar to rectangular. And so basically, what you just need to know is that our complex number S, it can be represented on the S plane here as having a real part and an imaginary part. And so here, basically, if we have our S right here, and so if we draw a vector from the origin all the way up to that point, that can be represented as the magnitude, so the length of that vector, and the phase angle, so the angle between the real axis and the vector. And now that we discussed that, some examples per se of our rectangular format, or also known as Cartesian. So if we have 1 plus 1j, this is in Cartesian form. If we have just 1, notice that it's just a real part, and there's no phase angle because it's implicit. So this would just be referencing, if you think about your plane here, if it just said 1, it would just be 1 unit on the real axis. So this is Cartesian because it's the real part, but it can also be considered expressed in polar form because the angle is just 0. It's on the real axis here. And then we can have -1 for S. And so if they say -1 here, that means we're in the negative region of the real axis. And so notice that this is given in Cartesian form because we have the real part. And then they don't give us a phase angle. Notice the phase angle is 180 degrees. So this is only Cartesian. It's not polar. And then the polar form, 1 angle of pi. So that would be the exact same thing. Notice here. So this would be an angle pi from the real axis, 180 degrees, and the magnitude is -1. Sorry, 1 unit. So it's 1 unit to the left of the origin. So this is not in Cartesian form because they gave us a phase angle. It's in polar form. So notice how you can represent all these, and it really depends on how it's given to you, the complex number. Here it's in Cartesian because they give you an imaginary component. Here, because the angle is 0, it's implicit, so it's both polar and Cartesian. Here it's a -1, so it's just Cartesian because it's an angle 180, which isn't specified. Where here they specify the angle, so it's just polar. Okay, so now we're going to look at complex functions. So g of s equals, and then what we're going to see, complex function is you have a function numerator and you have a function in the denominator of s, which is a complex variable. And so what a complex function does is it takes in a complex number as its input, and it generates another complex number at its output. And so that's what we're going to see here. So a complex function basically can have magnitude and phase. So here's our complex function, g of s. And if we're going to find the magnitude of g of s, that's going to equal the magnitude of our numerator all over the magnitude of the denominator. And then if we have to find the phase of g of s, that's going to be the phase of the numerator minus the phase of the denominator. Okay. And so let's say our example basically is find the magnitude and phase. So find magnitude and phase, and then it's going to be of g of s is equal to k s plus z1 times s plus z2 all over s plus p1 times s plus p2. Okay, so if we have to calculate the magnitude here in the phase, if we have to take the magnitude, what I would literally do is just take the magnitude. So take the magnitude of everything in the numerator, and then take the magnitude of everything in the denominator. And so remember, here, basically what we're going to have is this would become then here, if you look at each part, remember, S has a real part and an imaginary part. S has a real part and an imaginary part. And so what you're going to have to do is remember how when you take the magnitude, you take the square root of the real part plus the imaginary parts, square root of the real part squared plus the imaginary part squared. So here, basically, if we're looking at g of s, and s, remember, is equal to sigma plus j omega, you would put inside of here, j of s is equal to, okay? And then a lot of times, I will just say this, they'll say find the magnitude and phase, and then usually it's the frequency response. So we'll get into this later where they just assume s is equal to j omega, but here we'll just do the real part squared plus the imaginary part squared. So this would be the square root, and then this would be sigma plus z1 squared, and then plus omega squared. And then here we would have square root of sigma plus z2, so the real part squared, plus the imaginary part squared. And then here in my denominator, I'm going to have square root, and then it's going to be sigma plus p1 squared plus the imaginary part squared. And then I'm going to have sigma plus p2 squared plus the imaginary part squared. Okay. So then that's good. And now what we have to do is we're going to have to find basically the phase angle of this. And so notice here, what you could do is we could have written this exactly the same format because this is just a constant k. So depending on the value k, square root of k squared. And so then you can get the actual length of that, the magnitude. So now what we're going to do is if we want to find the phase angle of g of s, it's going to equal, okay, well, the phase angle it's dependent upon is k positive or negative. And so if k is positive, it's going to be 0. So that's when k is greater or equal to 0. But when k is negative, it's going to be 180 degrees because it's going to be on the negative real axis. It's not going to be on the positive side. So it's going to be a phase angle 180. And so this would be 180 degrees when k is less than 0. and then plus, and then in our numerator, we're going to have tan inverse, and then our imaginary part is omega all over, and then here we have sigma plus z of I, and then plus, and then our second part is going to be tan inverse omega all over sigma plus z of 2. And then notice in our denominator here, we're going to subtract, so minus tan inverse. Then it's going to be omega all over sigma plus p1. And then the other one in the denominator, minus tan inverse omega all over sigma plus p2. Because these terms are in the denominator, remember they subtract p1 and p2, so that's why we have the minus sign in front of the tan inverse for those two. Okay, now that we talked about that, what we're going to see specifically is if he wants you to find the magnitude and phase of g of s is equal to s plus 1 all over s times s plus 2. Okay. So, and he's going to evaluate it at a point at s1 is equal to -3 plus j4. Okay, so what we have to do is we're going to have to find the magnitude and phase. So here, what's going to happen is if we have to find the magnitude of g of s of 1, it's going to equal. Well, here we know basically in our numerator, we're going to have to find the magnitude of the numerator and magnitude of the denominator. Okay. And these are all S1 in here because we're evaluating it at S of 1. And so we're going to plug in our S1 here. And so plugging in our S1 term into the equation for S1, so plugging that value in, we're going to get -3 plus j4 plus 1. Find the magnitude of that. And then -3 plus j4, -3 plus j4 plus 2. Okay, now when we evaluate this, we can simplify it right before taking the magnitude. So this would be in our numerator, going to be -2 plus j4. Then in my denominator, it's going to be -3 plus j4. And then it's going to be -1 plus j4. And so now, when we have to find the magnitude of this one, what we're going to have is g of s of 1 is going to be equal to, and then here we have to take the square root, and then this is going to be -2 squared plus, and then 4 squared all over, and then what we're going to have in denominators, we're going to have square root, then it's going to be -3 squared, and then plus 4 squared, and then we're going to have the square root, and then this is going to be -1 squared plus 4 squared. Okay, so when we evaluate this, what we're going to get is this would be 4 plus 16 square root of 20 all over, and then here this would be 9 plus 16 square root of 25. And then here it would be 1 plus 16, so that'd be square root of 17. And then when you plug this into your calculator, what you're going to get is square root of 20 divided by, and then square root of 25 times square root of 17. Gonna get 0.216, basically. 0.217 if you round. Okay, so we found the magnitude, and now we need to find the phase. So phase of g of s of 1 is going to equal. So we have to find the phase of the numerator. So here, what we're going to do is when you have to find the phase of the numerator, remember it's going to be tan inverse because we're in the numerator. The imaginary part was 4 all over the real part, which is -2. And then in our denominator, minus tan inverse. The imaginary part was 4 all over -3. And the other pole in the denominator, it was going to be minus tan inverse of 4 all over -1. Okay, so this is where you have to be careful when you take the tan inverse because you have to pay attention to the sign. And so when this is saying, remember, it's tan inverse of the imaginary part all over the real part here. And so what we should expect for this result is the imaginary part we're positive for, and then the real part is -2. So it's going to be somewhere over here for this result. So we should expect an angle that is over 90 degrees here. What we're going to expect, our imaginary part's 4, and then our real part is -3. So it's going to be over here. So we're expecting an angle over 90 degrees. And then here, we're going to have our imaginary part 4 and our real part -1. And so this is the angle we should be expecting over 90 degrees here to that point. And so when taking the tan inverse of 4 divided by -2, we get -63. Notice that's because tan inverse is limited between -pi/2 to pi/2. So you just add 180. So I get 116. So that makes sense because we're 116 over here. So 116.57 degrees. This one right here, if I do minus tan inverse and then 4 divided by -3, I get 53.13, which here, oh, that's because, watch this, tan inverse of 4 divided by -3 is -53, but add 180, you get 126, and remember the negative sign in front, so multiply by -1, you get -1, 26.87 degrees. Then here, tan inverse of 4 divided by -1, you're going to get -75.96, add 180, and then remember minus sign in front, so minus 104.04 degrees. Okay, so 116.57 minus 126.87 minus 104.04. You get -114.34 degrees. Okay, so that is our phase. So we found the magnitude and the phase. So if we represent this on a polar plot, basically, we're going to see that from here, we have a 0 at -1. So at if we have 0, -1, -2, we have a 0 at -1, and then we have a pole at 0 and a pole at -2. And we're evaluating at this point -3 plus J4. And so this is assuming here basically -3 would be over here, and let's just say this is that is J4 right there. So this is your point S1. And so what we're doing here is we're basically just trying to find the magnitude. So we're finding the contribution by each of these poles and zeros here. So this would be the magnitude of the first pole to that point, and then the phase angle of that first one. And then here, we're finding the magnitude of the 0 and the phase angle. And then here, we're finding the magnitude of the third one and the phase angle. So magnitude and phase angle. Okay, so how you can write this is if you're trying to solve for the magnitude of g of s of 1, it's the contribution. So remember, zeros are in your numerator, so it'd be m2, and then all over, and then what's in the denominator, your poles, the magnitude of the poles, so m1, m3, where when you solve for the phase angle, it's going to equal the phase of the 0, so that would be θ2. So θ2. Oh. Remember, θ2 would be in your numerator, so you just have θ2. Then minus what's in your denominator, the poles. So the angle of the poles are going to be θ1 plus, and then θ3. Okay. So you subtract the angle of your poles in your denominator. So that is just the method we did here. We found the magnitude of each of those vectors, and then we found the phase angle of each contribution. Positive for the zeros, so that's why it's positive in front, but negative for the poles, so that's why it's a minus tan inverse. Okay, so what we need to do now is we're going to look at first order systems. So first order system, it's basically a system with one pole. An example of that would be, let's just say G of S is equal to 5 all over S plus 2. If you look at this on your pole zero plot, you're going to notice at -2, you have a pole. And so that's what it's just trying to tell you. It has one pole, that's a first order system. So first order system has the following form. It's going to be G of S is equal to B all over S plus A. So it has one pole. That's what it's trying to tell you. And so what you can do is if you divide everything by A, so if you have B divided by A, all over S divided by A plus 1, and you're going to notice this is going to be in the following form, K over tau S plus 1, where your K is equal to B divided by A, and your tau is equal to 1 over A. Okay, so this form is preferred in industry because what this represents here, the K, is this is your final value, and the tau here is your time constant. And so what we're going to see basically is within here, your final value, if you have a unit step response here, and so if we're looking at the unit step response, your final value, this is your K, the final value that it approaches. And then your tau value is in order to get to 63% of that final value here. So at 0.63 of your final value, that's when you hit tau. And that's what's trying to tell you here. 63% of the final value, and then in numerator, that's your final value, if given in this form. So this is the general form for your first order system. It has one pole, and you can express it in this form. So a few important things about the graph of the unit step response is they like to talk about rise time, which is T of R, and that is approximately 2.2 tau. And so this is to go from 0.1 to 0.9 of the final value. And so that would be about, looking here, this is about 0.1 of K at that blue dash line. And then here's about like 0.9. So looking at the plot here, if I try tracing, the rise time is about here to go from 0.1, so 10% to 90%, the final value. The settling time is basically to reach and stay within 2% of the final value. So settling time for a first order system is approximately 4 tau. And it's to reach 2% of final value and stay. So that means it does not go outside of that 2% after hitting that point. So for us, looks about like 90% of the final value would be right around here, which is about here, I would say. That's your settling time to get to 98% of the final value. And so that's pretty much it. So if you have to calculate any of these, for your first order system here, if you were to calculate what is the rise time, what's the settling time, just convert this so you get it in the format. So divide everything by 2, so you get 5 over 2, and then it'd be S over 2 plus 1. Now it would be in this format. So your tau is 1 over 2. So to find the rise time, it'd just be 2.2 times 1 over 2. So that would be 1.1. And the settling time would be 4 times 1 over 2, which is 2. And so you can calculate both those. And now that we talked about that, we're going to get into second order systems. So second order systems have two poles. So basically a system with two poles instead of just one. And so an example would be G of S is equal to, and then this is 1 over S plus 2 times S plus 5. Okay, so notice that there's two poles here. If you were to graph this, one pole's at -2, one pole's at -5. There you go. And so a second order system can be represented in the following form. So it's omega n squared all over s squared plus 2 zeta omega n s plus omega n squared. So that's the format of a second order system. And so sigma here is known as the damping ratio. And then the damping is given by sigma d, and that is given by sigma omega n. So this is the damping here. Omega n is known as the natural frequency. And then we're going to have omega d is going to equal, and then that's omega n square root of 1 minus zeta squared. And so here, this is known as the damped natural frequency. So notice it takes natural frequency, and so it's the damped natural frequency. Here's just the damping, and then we know sigma determines our damping ratio and natural frequency here. And so if you solve for this denominator, what you're going to get for your poles, basically, so the location of your poles, notice it's to power 2, so you're going to have two poles. So location of your poles is going to be given by, when you take the quadratic of this, it's going to be negative sigma omega n, and then plus minus j, and then omega n square root of 1 minus zeta squared. Okay, so what you're going to notice is you can also represent this, because this part here is your sigma d, and this part here is your omega d. So this is equivalent to negative omega d plus minus j omega d. Or what you can do is you can represent this in polar format, where it's omega n, and then it's going to be the phase angle of pi plus or minus theta. And so if you take the square root of this, you get omega n. Basically, if you take the square root of the real part squared plus the imaginary part, you'll get omega n for your magnitude. And then finding the phase angle. Important thing to note here is theta is equal to cosine inverse of zeta. And so let's just look at this on a pole zero plot so you guys can better understand it. So here we have our real part sigma and our imaginary part j omega. And so when we have to plot the poles of the system, we're going to have negative zeta omega n for our real part. And our imaginary part is going to be given by j omega n square root of 1 minus zeta squared. And so looking at the intersection of the two, right here, that's where our pole is going to be located. So one of our poles, and then the opposite poles just on the opposite side. So this would be negative j omega n square root of 1 minus zeta squared. And so this would be using the Cartesian form. If we use the polar form, it's going to be omega n. So drawing our vector here. This is omega n. And then your phase angle is right here. So be careful, it's not from the real axis to the vector, it's from the negative real axis to your vector. So just be careful there. And so what we see here is you have a plus minus theta because your opposite pole is located at the same magnitude, omega n, but it's now going to be negative theta. And so because your complex pole is at the opposite end. And so that's basically where your two poles are located. Now, a very important thing is when you have your damping ratio in this equation here, your damping ratio is going to determine the response of your system. And so zeta can equal 0, zeta can be between 0 and 1, zeta can equal 1, and zeta can be greater than 1. So when zeta is equal to 0, you have, is completely, watch, is zeta 0, you have no real axis component. You're literally just on the imaginary axis. So your poles here, if we graph each of these, and then for zeta equals 0, you're going to be on the imaginary axis. For zeta in between 0 and 1, you're going to be in between the real and imaginary axis. And when zeta is equal to 1, you're going to have a repeating pole. When zeta is greater than 1, they're going to start to split off. And so this response, when you're on the imaginary axis, it's completely oscillatory. So what we're going to see in the response here is it's going to be completely oscillatory. So notice that we have an oscillating waveform. So this is known as an undamped, where here when we have the poles in between, this is going to be our underdamped. And so looking at it, the response, notice it's going to oscillate at the beginning and then it's going to slowly die out. So this is known as underdamped. These oscillations start to decrease over time. And then we have critically damped, which is right here. So critically damped, it's going to follow the following format. So critically damped, and then over damped. So that would be our last scenario here, where this one is just going to be faster. And notice that's going to look more and more like a first order system. It's going to just be faster, overdamped system. And because it looks more like a first order system, because notice that we're just along the real axis here. We're not along the imaginary axis anymore, so we're going to just have real roots for our denominator. And so then it'll look more and more like our first order, because they're going to be further apart, so you can just estimate it by the pole that's closest to the j omega axis. So then you can convert the second order into a first order system just by using the simplification. Okay, so just like with a first order system, the second order system, a lot of times we like to look at the underdamped response. And so that's given by the following. So let's just look at that. So the underdamped looks like the following here. And so they like to talk about rise time. So T of R, remembers rise time. That is basically from 0.1 to 0.9 of final value. And so if we're to calculate the rise time here specifically, it's going to be, well, our final value is going to be at this point right here. So that's our K right here, the final value that we approach. But from 0.1, that's going to be about here, I would say, 0.1. And then 0.9, if this is the final value, your 0.9 is going to be about here of that final value. So that's 90%. So I would say that if we were to guess this would be about the rise time in between those two intervals right there. And then the settling time is to reach and stay within 2% of the final value. So reach and stay within 2% of final value. So here, in order to calculate that, the final value is here. So in order to get in within 2%, we're going to be right, it looks like around here is where 2% mark is. So that would be right around here at the settling time. So it's going to be 2% of the final value, which looks about here. And then our next one is going to be the time to peak. So when we hit the peak point. And so that's given by the equation. Oh, settling time does have an equation, so we know, just like in how we had an equation for the first order, for the second order, it's going to be given by 4 over, and then it's going to be zeta omega n, just so you know. Time to peak is basically the time to hit this peak right here. So that's your time to peak. And so that's to get to the peak value. It's given by the equation pi divided by omega d. And remember, your omega d is going to be omega n square root of 1 minus zeta squared. Okay. And then your percent overshoot, that's basically how much did you overshoot your final value by. And so here what we're going to see is that's going to be given by the equation 100 e to the negative and then pi zeta all over square root of 1 minus zeta squared. And then when you solve for zeta, it's going to equal negative natural log of percentage overshoot divided by 100 all over square root of pi squared plus and then natural log squared of percent overshoot divided by 100. Okay, so that's how you solve for all that. And there is an important relationship. What we're going to see is when you have a higher zeta, you're going to have a smaller percent overshoot. And so if you basically have your table, what you're going to notice is when you compare your zeta versus percent overshoot, for zeta 0 0.9, 0 0.8, 0 0.7, 0 0.6, 0 0.5, 0 0.4, 0 0.3, you can use the table. So if you know your percent overshoot has to be less than 0 0.2, then your zeta must be 0 0.9 or greater. If your percent overshoot must be less than 0.8, then your zeta must be 0.8 or greater, and then etc. So that's what this table is used for, is basically if you know your percent overshoot must fall within a certain range, you can calculate, you can just look at the table and estimate that very quickly. And so that's what we have here. So now that we can just easily use that table, what we're going to see, if we do a design problem in order to test it out, what we'd have to do is say that we need okay, this one I think is a good example. Find K such that the percentage overshoot is less than 5%. Okay, and then they give us our input, which is theta, and then we have our block diagram. So within here, this goes through K, and then we go for 1 all over S times S plus 2. And then we have theta S as our output. Okay, so here if we need to find K such that the percentage overshoot is less than 5%, what we're going to do is first we need to calculate our system. So our T of S is going to equal, okay, the forward path, which is K all over S times S plus 2 all over 1 plus K all over S times S plus 2. Okay. So here, this is going to be our transfer function. And so what we need to do, simplifying this, is going to be k all over s times s plus 2 plus k, which is going to equal k all over s squared plus 2s plus k. And so now what we're going to do is notice that within here, our second order system, this value right here is going to be 2 zeta omega n. And then remember that this last position here is omega n squared. And so if we need our percentage overshoot to be less than 5%, and so looks like zeta needs to be greater than 0.7. So what we can do here is we are going to let zeta equal 0.7, because that would give us our criteria right here. If it needs to be less than 5%, 0.7 zeta or greater is going to give us 5% or less overshoot. So chose it right here. And then notice that our 2 zeta omega n is going to equal 2. So simplifying zeta omega n is equal to 1. And then plugging in our value zeta, because we know it's 0.7. So 1 divided by 0.7. What that's going to give us is, let me check, 1 divided by 0.7. We get 1.428. And then remember, your omega n squared is going to equal your k. Your k is equal to your omega n squared. And so your k is going to equal 1.428 squared, which I got was 2.04 for my k. So that's how you can find your value of k, just from a second order equation. And so now that we got that, let's look at an example where we need to find the region on the left-hand plane where the poles of the second order system have the settling time less than 1 second and the percentage overshoot less than 10%. Okay. So what we have here is we know that settling time for a second order system, remember, this is 4 divided by zeta omega n is less than 1. And then your percentage overshoot, when it's less than 10%, looking back up at our table, if we need that, zeta must be greater than 0.6 about. That's what we're seeing. So that's what we can just get from our two parameters. Now, if we know this, what we can do here is remember that zeta is equal to cosine of theta, or theta is equal to cosine inverse of zeta. So what we have here is zeta must be greater than 0.6. And so since zeta is going to be on this side, what we're going to have for angle is our angle must be, it can be greater than or equal 0.6 because that'll give us our percent overshoot. So zeta can be less than or equal to cosine inverse of 0.6. And so what we're going to see here is cosine inverse of 0.6 is going to give us 53.13 degrees, okay? And then here, when we solve, we're going to get 4 must be less than zeta omega n. And so then if you rewrite it, so 4 is basically on the right-hand side, what we're going to get here is if you multiply through by -1, remember that flips the sign. And so here, what we're going to have is if you draw this out, remember that your negative zeta omega n is on the left-hand side. If you recall from the second order systems, negative zeta omega n is your intercept here, basically, on your x-axis. So -4 here. And then your angle is less than or equal to 53.31 degrees. So here, your angle must be within 53.13 degrees. So it has to be less than or equal to that. And so recall that if you have conjugate poles, it will be on the opposite side as well. So that's why we have to draw it. Also negative theta, so negative 53.13 degrees. And so this -4 restricts it that it must be past this point right here, not including, and it must fall within this region of the angle. And so then your value here is basically you can have your poles anywhere such that they fall beyond the -4 and they fall within the 53.13 degrees. And so that's how you would find it. And so now that we talked about that, we're going to talk about approximating higher order systems. So in order to approximate higher order systems, this refers to like third, fourth, fifth, sixth order. So basically, if a pole is closer to the j omega axis by 1/10 the distance of the other pole, the system can be approximated by the pole closest to the j omega axis. So here, what this is just trying to tell you is basically if we have a pole right here, then we have a pole all the way out here. So the distance this one is to the j omega axis, I'm going to call D1. I'm going to call the distance to this pole D2. If D2 all over D1 is greater than or equal to 10, then you can approximate just by D1. And so when you approximate, you have to ensure the DC gain. So that would be G of 0 matches. And so you don't change the DC gain. And then what you also have to do is you can have pole zero cancellation on the left-hand plane if pole is very close to 0. Okay, so let's look at what that means, basically, for some examples. So here, what we're going to see is, let's look at, if we're given a second order system, G of S is equal to, and then here we have 500 all over, and then we have S plus 20, then S plus, and then 4S plus, and then this is 20 here. Okay, so we know if we're graphing this, one pole's at -20. And then here, remember that this term is 2 zeta omega n. And so your zeta omega n is 2 from this because just 4 is equal to zeta omega n. Zeta omega n would be equal to 2. So remember, on this, it's negative zeta omega n. So at -2, you're going to have your complex conjugate poles here. So these would be two complex conjugate poles at -2. Well, the distance, if you look at the distance between the two, the distance here for D1 versus D2 from the j omega axis. And so here, your D2 all over D1 is going to equal 20, 20 all over 2, which is equal to 10, which is greater than or equal to 10, so you can approximate the second order system. And so if we approximate it, g of s is going to equal 500 all over, and then here, this one, oh, sorry, because it's a second order, there's two poles. Here, it would cancel out this one, so you'd have an s squared plus 4s plus 20. But let's make sure this is correct, because we have to look at the DC gain. So from here, the DC gain, without the approximation, g of 0, substituting in 0, you have 500 divided by 20 times 20, which would be 400. So 500 divided by 400, you got 1.25. So we have to make sure the DC gain matches here. So 500 divided by 20 here, that would only give you 25. And so in order to get the same DC gain, if you divide the numerator by 20, what's going to happen is your g of 0 is going to equal 500 divided by 20 all over 20, which equals 1.25. So you get the same DC gain. So this would be your approximation. It is approximately equal to this. Okay, now, and we learned how to approximate it. Let's look at pole zero cancellation. So for g of s is equal to s plus 2.05 all over s plus 2, and then s plus, and then here we have 20, and then s plus 200. What's going to happen here is basically, do we have pole zero cancellation? Well, let's check. When we plot the poles and zeros here, and we're going to have a 0 at negative 2.05. We're going to have a pole at negative 2. Then we're going to have a pole at negative 20 and negative 200. So just say this is negative 200, this is negative 20, and this is negative 2. And so right here, we're going to notice the poles are very close to the 0 because 2.05 is close to 2. So we can cancel these because they're both on the left-hand plane. So your system can be approximated. But when we approximate our system here, g of s is equal to 1 over s plus 20 times s plus 200. Notice that, hey, wait, this pole, isn't that like this one is 10 times the distance compared to this one? So you can actually delete this one here. And so because it's 10 times distance, so we can just approximate it with s plus 20. And so this is our approximation because we're able to use pole zero cancellation and approximate it because this pole was greater than 10 times the distance of this one. And so now we need to make sure the DC gain matches. So on the original system here, our DC gain was equal to, and so when we had here, it'd be just 2.05, and then 2 times 20 times 200, which this is equal to, if we look at that on a calculator, 2.05 divided by 2 times 20 times 200, we get this number right here. So it is going to be approximately 256.25 micro, where here we have 1 divided by 20, and so which is only 50 milli. So we have to make sure DC gain matches. And so what we have to do is basically, if you multiply this by if you multiply numerator by 2.05, then you multiply the denominator by here 2 and 200, your G of 0, this is for the approximated system, I'm just going to call this approximated so it's easier, is going to be approximately 2.05 divided by 20 times 2 times 200, which it will give us the same DC gain of 256.25 micro. And cleaning up this approximation so it looks better, 2.05 divided by 2 times 200. You would get 0.005125 divided by S plus 20. So that would be your approximation right there for your DC gain. And so now, basically that we had that, and we're going to see a lot of times we have to calculate steady state error. And so when we have to do steady state error, how do we calculate that? So steady state error basically is like the difference in the final value versus what we want. So a lot of times when we calculate steady state error here, if we have our second order system and it goes to a certain value, say here, but our value that we actually wanted was right here. So there's going to be a little difference in the error. So our final value does not match what we want for final value. So this difference here between the two is known as the steady state error because you didn't approach the value you wanted in the end. So steady state error is defined as the limit as t goes to infinity and then e of t. And using the final value theorem from the Laplace table, you can write it in this format here. And then recall that basically E of S is equal to your input R of S minus your desired output. And so your E of S is equal to R of S minus C of S. And so if you look at a unity gain feedback system, so this is for unity feedback, you can write it in this form. If you just substitute in for your E of S, you can write it as the limit as S goes to 0, S1 over S plus G of S, R of S. And notice that each type of input has a certain way that it affects the steady state error. So if you have a step input, that's 1 over S. If you have a ramp input, it's a 1 over S squared. And if you have a parabola, it's 1 over S cubed. So each input's going to affect your steady state error. And so notice that this is only for unity feedback. So I don't like writing this one a bunch. I like writing it in this format because this is a general format. And then I solve. I just look at my unity feedback system here. And then I determine, hey, what is E of S? I just do R of S minus C of S. And then when I plug that in, when I solve for C of S, remember C of S is just your R of S times your system. And then you can solve for it in this way. And so basically, we've been talking about unity feedback system. So let's just do the block diagram of it. A unity feedback system has the following format where your G of S, your system, and then here's your output C of S. And then here, this is known as your error, E of S, right here. The point from your R of S minus your C of S. And so now, a lot of times, what we like to look at is how many peer integrators we have in our system. And so our system type refers to the number of peer integrators in the system. And so looking at this, peer integrators, when I talk about that, that refers to 1 over S terms. And so if we have our G of S is equal to 1 over S cubed times S plus 2 times S plus 5, what's the system type? And so our system type, which I'm going to indicate by I, there's 3 peer integrators. These are not peer integrators here. So I is equal to 3. And so what about this system type? If we had g of s is equal to 5 all over s plus 2, I don't see a pure 1 over s term, so this I is equal to 0. So we're going to get a chart, basically, that tells us for the unity feedback system, what is the steady state error. And so within our chart, we'll basically have the system type, which is going to be 0, so no pure integrators, 1 pure integrator, or 2 pure integrators. And then we're going to have the type of input we're going to have. And so if we have a unit step, which is 1 over s, if we have a unit ramp, which is 1 over s squared, or if we have a unit parabola, which is 1 over s cubed. The steady state error for a unit step, if you have no pure integrators, is going to be 1 over 1 plus kp. For the unit ramp, for 1 pure integrator, it's 1 over kv. And then for the unit parabola, it's 1 over ka. And so here what we're going to notice, basically, is when you have one basic in your table, when you have 1 pure integrator, for unit step input, you're going to have 0 steady state error. When you have 2 pure integrators for unit step input, you're going to have 0 steady state error. But for your unit ramp, when you have 0 pure integrators within your system in your inputs to unit ramp, you're going to have infinite error, steady state error. But when you have 2 pure integrators, it's going to be 0. But then here for unit parabola, it's going to be infinite here. Sorry, let me reset. This one's going to be infinity. You have infinite steady state error until you get 2 pure integrators. Then you can actually determine how much steady state error you have. So you're probably wondering what Kp, Kv, and Ka are. Kp is known as the position error constant, and so that's given by limit as s goes to 0, g of s. Then Kv is the velocity error constant, which is given by limit s goes to 0, s g of s. Notice that velocity is a derivative position, hence the s to indicate derivative. And then Ka is known as the limit as s goes to 0, then s squared g of s. So you take, basically it's s squared, you take the derivative again of velocity, get acceleration. So this is your acceleration error constant. And so let's look at an example where we're given the following system. So for our system, we're going to have our R of S, and then it's going to go through to summing block. And then here, our G of S is going to be given by 50 S plus 1, S plus 5, all over S plus 3, and then S plus 4. And then we're going to have an S here. And then our output is C of S. And notice that this is a unity feedback system, so therefore we can use the table because this table works for a unity feedback system. If it's not given in unity feedback, you have to convert it to unity feedback system. And so this table only works when it's a unity feedback system. So here we have our unity feedback system. And so the system type, what is it? 1. And the steady state error, if we have to calculate that, so it's going to say calculate the steady state error for step, ramp, and parabola input. Okay, so notice that we have a pure integrator of 1. So we're going to have 1. And so we have to calculate the steady state errors for the step, the ramp, and the parabola. Looking at my table, we know for the step, basically, the steady state error is going to equal 0 from the table. And when we have the parabola, so this would be for the step. When we have the parabola input, it's going to be 1 over kb. And so this one, so for parabola, if we have to calculate kv is equal to the limit of s g of s as x approaches 0. And so that's going to be the limit here, if we cancel the s with the s and our g of s, because this is our g of s right here, we're going to get s approaches 0 of, and then this would be 50 s plus 1 times s plus 5 all over s plus 3 times s plus 4. So we just canceled the s here with the s in the denominator here. And so now plugging in 0, what you're going to get is you're going to get 50 times 1, which is 50, times 5, which is 250, all over 12. And so 250 divided by 12, we're going to get 20.833, which is going to be 125 over 6. And so then your steady state error is 1 all over 125 divided by 6. So that's going to be 6 over 125 for your steady state error for the parabola. Now, if we have to calculate the steady state error for, sorry, this is for the ramp. My bad. Ramp. Now we're going to calculate the steady state error for the parabola, and notice that it's infinity. And so our steady state error is going to be infinity for the parabola. So that's just using the table. So make sure you have a table on your cheat sheet. But notice that this table only works for unity feedback. So if you're given your system and you have a feedback, convert it into unity feedback in order to use the table. If you basically don't want to do that, then you're going to have to calculate the steady state error here. Just plugging in for your E of S, you can do the input minus the output, and then plug it in here. And so you would calculate, remember, your output here, C of S, is equal to your input times your system. So you can always calculate it that way and just hard solve it for the steady state error if it's not a unity feedback system. Now that we talked about that, we're going to look at when a system's stable, marginally stable versus unstable. So a system is stable if the closed loop poles are on the left-hand plane. And so then it's unstable if one pole of the closed loop system is on the right-hand plane. And then it's going to be marginally stable if all poles of the closed loop system are on the left-hand plane or on the j omega axis. But be careful, because if it's on the j omega axis, they're simple. And what do we mean by simple? Simple poles, they're not repeated on the j omega axis. So you can't have two on top of each other. And so what we're going to see here basically is within our graph. Here we know in this region it is stable. So this is the stable region. This is the unstable region. And when you include the j omega axis here, this is marginally stable. Because it's marginally stable because you can't repeat them on the j omega axis. So you can't have like two at the same point. If there's two right at like positive j2 here, if there's two poles on the j omega axis at the same point, then it is unstable. But it is marginally stable if there's only one. So say there's just one at J2, then you're fine. But you can't have two repeated there. And so what we're going to do is we're going to determine the stability of the following system. So our system is going to be given to us by R of S. This is going to be input here. And this is going to be our EVS. And then we have 3 all over S minus 1, S plus 2. And then it's going to go through to our output, C of S. And then we're going to have our feedback here. So our transfer function, T of S, is, remember, all these require closed loop, closed loop, closed loop. So you can't calculate it on just the open loop system. You have to first calculate the closed loop system. So T of S is equal to, and then when you solve this specifically, you're going to get 3 all over S squared plus S plus 1. And so what you're going to have here is you're going to have, if you solve this denominator, if you use the quadratic equation, you're going to get 2 poles at -1/2. So you're going to get 2 conjugate poles at -1/2. And so what we're going to see here is these poles are on the left-hand plane. And so this is a stable system. So be careful. What this example is just trying to show you is even though for the open loop system, there is a pole on the right-hand plane, its stability is defined by the closed loop poles. So just be careful and make sure you find the closed loop system, and then the closed loop system, find the poles of that, and notice that this is stable because the poles are on the left-hand plane. And so now that we talked about that, we're going to look at the Roth-Hertz table. So the Roth-Hertz table, or known as the Roth-Hertz test, basically tells you the number of sign changes equals the number of unstable poles. So what we're going to see is we're going to have your transfer function, T of S, is equal to some numerator polynomial all over a denominator polynomial, which we call the characteristic polynomial. So there's a polynomial numerator, but what we're interested in is this term right here, which is known as the characteristic polynomial. And so this characteristic polynomial, we're going to look at an example of basically how you form the Roth-Hertz table, because I think that's the best way of learning it. So if your T of S is given to you, and you have it equal to 200 all over, and then here we have S to the power 4 plus 6S power 3 plus 11S squared plus 6S plus 200. So for the Roth-Hertz test, what you have to do is basically here where you have your S to the 4, you drop the power S3, S2, S1, S0. Okay? And then looking at your coefficients of your denominator. So you look at the to the even power for S to the 4. So the coefficient here is 1. Coefficient of the even power is 11. Coefficient of an even power S0 is 200. Now coefficients of your odd terms are 6 and 6. So to calculate this point right here, what we're going to do is you have to take, so I'm going to call this, basically you have to do the determinant. And so you're going to do 1 times 6. So 1 times 6 minus 6 times 11 all over what's in this spot right here in the bottom left, which is 6. And you take the negative sign of that. And so -6. And then to calculate this spot here, it's going to be 1 times and then 0 minus and then 200 times 6 all over what's in the bottom left spot, which is take the negative of that minus 6. And so here what you're going to get is 6 minus 66 divided by negative 6. 6 minus 66 divided by negative 6. So 6 minus 66 divided by negative 6. I got 10. So for this spot right here, I got 10. And then for this spot right here, 0 minus 200 times 6 divided by negative 6, you're going to get 200. Okay, so what's going to happen here is now you take the determinant again. So we're going to get, what you can do right here is you can actually divide everything in the row to just make it simpler. So you can divide the entire row by 10. So that would give us 1, and that would give us 20. So now what we're going to do is when you try finding this spot, it's going to be 6 times 20 minus 6 times 1 all over negative 1. And then this spot here is going to be 1 times, and then we're going to have 0 minus, and then here it's going to be 0 times 1, and then divided by negative 1. So this would just become right here. This one is 0, we know, because 0. Where this one here is going to be 6 times 20, which is 120 minus 6, divided by, and then negative 1. So I got specifically, wait, let's look at this. 6 times 20. Yeah, so I got negative 114. So this term right here becomes negative 114. And then looking at my denominator here, what you're going to get specifically is your term is going to be 20 when you do that same calculation. And so now that you basically got everything, we have to look at the number sign changes in the first column here. So we're only going to be interested in the number sign changes here. So 1 to 6, there's no sign change. And then 6 to 1, which is here, this is just 1. I crossed it out and then made it 1. No sign change. 1 to negative 114. So that's a sign change. So we got 1 sign change from 1 to negative 14. And then negative 114 to 20, we have 2 sign changes. So 2 sign changes equals 2 unstable poles. So if we have 2 unstable poles, notice our characteristic polynomial is 4. So that must mean the rest of the poles are stable. So we have 2 unstable poles, and therefore we must have 2 stable poles. Okay. So that's how what the Rock-Hertz tells you. There's 2 special cases, though, you have to watch out for on the Rock-Hertz table. So the special cases, so this is our answer for the previous one, so let me just box that, is for the first special case is if you get 0 only in the first column. So say if you have a 0 here, but we had positive, or we had other values, other numbers there, then you substitute with epsilon. So you cross out that 0 and you substitute with epsilon, and you treat it with the same sign as the one right before it, and then keep that sign. And then case number 2 is that you have an entire row zeros. So that would mean, like, say, what if this was 0, 0, 0? And so what you do is you have to look at the row before. So you look at the row before. So if we're looking at row 3 and is all zeros, you look at row 2 and you make that, set that equal P of S, and you take the derivative of it. So you take the derivative and then you substitute that in now for your row 3. And so then that's how you would proceed with that one. And so if you have entire row zeros, or if you have 0 in the first column, that's the special cases, which were covered in the other video for 370. So you can watch that one if you need a review on that. So now that we talked about that, That's basically everything on the review side. Now we're going to get to the root locus method. So your root locus, just so you know, is going to be the path of closed loop poles as k is varied. So let's look at what this means really. And so what we notice is when we have an example where we have our R of S, then goes into a summing block here. And then we have our K, then we have our G of S. Then we have our output, which is C of S here, and then we have it closed off. So if G of S is equal to 1 all over S times S plus 2, we need to plot the open and closed loop poles for K equals 0, 1, and 2. So what we have to do here is basically our open loop is just the for loop system. And so that would just be for open loop versus our closed loop. So this is going to be when K is equal to 0 here. It's just going to be 0. If we have that right here, what it's going to look like is, so right now we're going to have 0 times, and then that'd be S over S plus 2. And so in your denominator, if we look just at our numerator and our denominator, so if we're looking at our for loop system, for the open loop, L of S is equal to K times G of S, where G of S has a numerator, so K times a numerator polynomial all over denominator polynomial. And so this would be 1 all over, and then this would be S times S plus 2, and then times your K. And then your closed loop system, just so you know, is T of S is equal to Kg of S all over 1 plus Kg of S. And so remember, your G of S has a numerator and a denominator polynomial. So you can write that as K numerator of S all over D of S all over 1 plus K N of S all over D of S. And so right here, what we see is this is going to equal, we're going to have K N of S all over D of S plus K N of S. Okay. So we know the transfer function, basically for this one is going to be 1. So this would be K times 1 all over, and then this would be RS plus 2 plus K times 1. And so this would be, if we just substitute in for N of S, the numerator G of S is 1, and the denominator G of S is S times S plus 2. So this would be S times S plus 2, which is going to be K all over S squared plus 2S plus K. And so when we look at here, when we have to graph, when K is equal to 0, what we're going to notice for the open loop system, when our K is equal to 0, numerator is going to be 0, but we just have 2 poles, one at 0, one at -2. And when we graph the closed loop system, when K is equal to 0 here, this is going to be we're going to get our S times S plus 2. Then we have a 0 in our numerator, but notice we have 2 poles, one at S, one at S plus 2. So notice when K is equal to 0, your open loop is equal to your closed loop when K is equal to 0. Now when K equals 1, substituting in for your L of S, it's going to equal 1 all over S times S plus 2. And then your T of s for your closed loop system is going to equal, this would be 1 over s squared plus 2s plus 1. And so what you're going to notice is when you solve this denominator, you're going to get two poles specifically at -1. But here, your poles are going to remain in the same location at 0 and -2. 0 and -2. Where here you're going to get two repeating poles at -1. Now, when you increase k to 2, your L of s is going to become 2 all over s times s plus 2. And then your T of s is going to equal, and then here we have 2 all over s squared plus 2s plus 2. And so when we plot this one, your poles are going to still remain in the same location here. So you're going to have it at 0 and -2. But for your closed loop system, your poles are going to change. They're going to go to basically -1 plus j, -1 minus j, when you just take the quadratic of that denominator. And so notice that your closed loop system is changing. It is going, what we see is it's going this way and this way. And so over time, the two poles come together and then they go outwards. And so that's what we see here where the open loop poles, it's not changing with our k. And so basically, that's what we say. The root locus is the path of the closed loop poles because that changes when the k is varied. So as k increases, we notice that it's changing here. But when k is not increasing, it's staying the same. When k is changing for the open loop system, it doesn't change. But for the closed loop system, it does change the path of the root locus. And so what we're going to see here is within the root locus, basically, there's a set of rules that you have to follow. Is when we talk about the root locus, it's the set of values for which, so root locus is the set of values for which 1 plus kg of s is equal to 0 as k is varied. And why did I write this equation right here, 1 plus kg of s is equal to 0? Because remember, our 1 plus k g of s, that is the denominator of our closed loop system, and that determines where the poles are. So when this is equal to 0, that's our poles. So that's basically saying it's the values for which the closed loop poles when k is varied. So that's the root locus. So the first thing basically here is the preliminary rules to the root locus. So preliminary rules. Number 1, basically, you write the characteristic equation. So basically, you do 1 plus k, and then your open loop system is equal to 0. And then you factor L of s in terms of poles and zeros. And so this would become 1 plus k times s plus z of 1, and then s plus z of 2, blah, blah, blah. And then s plus p of 1, s plus p of 2, blah, blah, blah. So you just factor it in terms of when you find your open loop system, you get the zeros and the poles, and you just plug that in. And then what you're going to do after is you're going to plot the open loop system. So literally from your open loop L of s, you literally just make a pole 0 plot. So here, if we do that, so say here, my Z1, your Z2, your P1, and P2, something like that. Z1, P1, Z2, P2, something like that, the locations. And remember, these are actually at negative, 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 negative z1, because s plus z1, when you set it equals 0, s is equal to negative z1, and then s plus z2 equals 0, it's going to be s is equal to negative z2, and so that's why. Then here's the rules for the root locus. So those are like all the preliminary rules, just write it in here. So rules for root locus. Number one is that the number of paths for your root locus is equal to the number of open loop holes. So see here how you have two open loop holes, that means you have two paths. So if we have g of s is equal to 5 all over s plus 3, s plus 2, s plus 4, we have 3 open loop holes, so we're going to have 3 paths. This would be 3 paths for the root locus to take. Okay, so the root locus is symmetrical. So when I say the root locus is symmetrical, that means that basically what happens here is, say that we have a pole, and then we have another pole, then we have a 0 and a pole. So this 0 in these two poles here, these are going to go this way, and then this one's going to go this way. Notice if you flip it, so if you flip, literally do it so that you flip this end over that way, it's going to be symmetrical with respect to the real axis. So you can just flip it all over. And then your next one is going to be for k is greater than 0, which we look at k greater than 0. The root locus lies to the left of an odd number pole or 0. So here, notice, as we start from the very right and we're going left, this is the first pole, or the first root, the second root, third root, and the fourth root. So the first pole, second pole, third 0, and then fourth pole. If you just say, okay, I'm going to count the roots as I go along here, you're going to see that, okay, to the left of the odd number, that's where the path exists. Here's the even number, there's no path in between. Here's an odd number, there's a path in between. And so it's just the root locus lies to the left of an odd number polar 0. And so you just start counting from the rightmost and you start doing it. And then what you're going to notice is that the root locus goes from poles to zeros. So it can be finite or infinite poles to finite or infinite zeros. This is just basically saying that up here, notice that went from a pole to a 0, and there's only one 0, so the other two poles went to infinity because there wasn't any other zeros. So it's basically using like a higher order system. If you approximate it, remember those zeros would be so far away that they didn't have any effect. But basically what's showing you is that it goes from poles to zeros, poles, and then if there's no more zeros, it goes to infinity. So that's what's trying to tell you. And then you need to determine the asymptotes. So find the asymptotes. So this is when it approaches infinity. So the asymptote center, which is given by sigma a, is equal to the sum from I equals 1 to n. And then this is negative pi minus the sum of how many zeros you have here. So this would be m. And then negative zj all over, and then the number of poles minus the number of zeros. And then your theta a is equal to 2r plus 1 pi all over, and then n minus m, when r is equal to, and then this is where you plug in 0 plus minus 1 plus minus 2. in order to find all your specific angles. So when they start repeating your angles, then you got all of them. So you just keep plugging in until you get how many angles you need to determine your asymptotes. And so basically this is just saying it's the poles minus the zeros all over the poles minus the zeros, the count of how many poles you have minus the count of how many zeros you have. So let's look at an example. So here, if we have g of s is equal to s plus 3 all over s times s plus 1 times s plus 4. If we have to determine the asymptotes, the asymptote center is going to be at, well, our pole here, we have a pole at 0 minus a pole, this pole's at -1, so plus -1, and then plus -4, and then minus, and then here we have a 0 at -3, and then all over the number of poles we have, which is going to be 3 minus number 0 is 1. And so that's going to be -5 plus 3, that would be -2 over 2, which would equal -1. And so that's where the asymptote center is. Now, if we have to determine the angle, theta A, when here, theta A, when r is equal to 0, it's going to be pi all over 2. So that would be pi over 2. And so that's when r is equal to 0. If r equals 1, it's going to be 3 pi all over 2. So theta A is equal to 3 pi over 2 when r is equal to 1. And then theta A, when r is equal to -1, you're going to get negative pi over 2 when r is equal to -1. And notice that, hey, pi over 2 repeats with negative pi over 2. So we don't need this one, actually. So we can stop because we determined how many that we had. And so our angles, we only had 2 angles because once we start increasing r, it starts repeating with the previous values. And so what we're going to notice is when you do the asymptotes, the center's at -1. So here, your center point is at -1, and you're going to have it go pi over 2 as your angle. So the first one is going to be at pi over 2. And your next one's going to be at 3 pi over 2. And so that's going to be basically your asymptotes because you have a pole at 0. You have a pole at -1. You have a pole at -4. And you have a 0 at -3. So if we look at the path, this pole is going to go to this 0, right? Because 1, 2, 3, 4, there exists a path right here. And then these two, they're going to go up in this direction. Basically, it's telling you one's going to go up with an angle pi over 4 from the real axis. I mean, pi over 2 from real axis. The other is going to go with an angle of 3 pi over 2 on the real axis, so one's going to go downwards. And so our asymptote is at -1, and so that's where line, the center asymptote, and it has an angle pi over 2 and -3 pi over 2. And then the next step is basically you find the breakaway and break-in points on the real axis. And so you're going to have k is equal to -1 divided by L of s. And so you take the derivative is equal to 0. This is where you just have to plug it into MATLAB sometimes because it might be really hard. And then from when you have your derivative equals 0, you find the point when it reaches its max. So that's where it breaks in or breaks out. So then you can then just plot it from there. And so notice that your break-in and breakaway, when I mentioned those, what those are is literally if you have 2 zeros over here and say you have 2 poles over here. And so right here. And so this would be the direction basically that you have. So this would be a break. a waypoint right there, break away, because you're breaking out of the x-axis and you're re-entering it at this point. So this is called a break-in point. So that's a break-in versus breakaway point. And then you can find the angle of departure and arrival at, so departure would refer to your poles, because you leave your poles and you approach zeros. And so this would be where your angle L of S is equal to 1 plus 2r times pi, where r is equal to 0 plus minus 1 plus minus 2. And so what we're going to notice here is you literally would just contribute. You find the contribution by each pole in 0. This one, I don't expect, so I'm not going to go over that. So now what we're going to do is let's do an example where we're going to look at, it's going to say plot the root locus for the system. Remember, when you plot the root locus, you're going to look at your open loop system. So if they give you your G of S, so they say find the root locus, make sure that you have the G of S, or the L of S, because your open loop system. Find root locus for, and then it gives us G of S is equal to, and then 1 all over S to the 4 plus 12S cubed plus 64S squared plus 128S. Okay. And so here, if you need to find the root locus, what we're going to notice is the first thing, number of passes equal number of closed loop, open loop poles. So how many poles do we have here? We're going to have 4. So we're expecting 4 pass because our numerator is degree 4. So we know we have 4 open loop poles, so we're going to have 4 paths. Next one, we're going to, root locus is symmetrical. So we know our root locus is going to be symmetrical here when we plot it. And so if we plot the poles and zeros, basically when you solve this, you're going to find that your first pole, when you use MATLAB, S1 is going to equal 0, S2 equals -4, S3 and 4 are equal -4 plus minus J4, okay? So we know the location of our 4 poles. When you use MATLAB command, I'll show you guys how to do that. Basically, so your sigma A, if we have to calculate, well, first we'll just plot the pole 0 plot of the open loop system. We're going to have 1 basically at 0, 1 pole at 0, and then we're going to have a pole at -4. Then we're going to have 2 poles at -4 plus J4, -4 minus J4. Okay, so we know all that, and now what we have to do is basically our sigma A here, because what we have to do from pole 0 plot, we know the path is going to exist to the left. So there's going to be a path here because going from the right, here's the first one, here's the second one. And so there's a path that exists right here. So we know that where it's going to exist, and it's going to go from the poles to zeros. Notice that there's no zeros though. So we have to calculate our asymptote. So sigma A is equal to, here our pole, one's at 0, one's at -4, and the other one's at -4 plus J4, -4 minus J4. And then all over, number of poles we have is 4, number of zeros we have is 0. J4 terms will cancel, and so we're just left with -12 divided by 4, which equals -3. And so our sigma A begins here. So basically our sigma A is at -3. So -3 here, and our angle. Angle A is going to be equal to, and then here we're going to have 2r plus 1 plus pi, or times pi all over n minus m. So when r is equal to 0, it's basically going to be pi all over, and then here we have 4. When r is equal to 0, when r is equal to 1, we're going to have 3 pi all over 4. When r is equal to -1, we're going to get -pi over 4. And then when it's equal to 2, we're going to get 4 plus 1, 5 pi over 4. And when r is equal to -2, we're going to get -3 pi over 4, which is the same as 5 pi over 4. So we're going to stop because this one is a repetition. And so we found that we had 4 angles here for asymptote. So basically, we know the center of the asymptote, and the first angle is going to be at pi over 4. The next one, so this would be angle 1, asymptote with angle 1 at pi over 4. Next one's going to be at 3 pi over 4. So going this direction. Next one's going to be at negative pi over 4. So going in this direction. And next one's going to be 5 pi over 4. So going in this direction here. And so what we're going to notice is that what we're going to have to do here is we're going to see basically that these two right here are going to go this way. When you use MATLAB, it's going to go this way, and then these two are going to go this way. So they follow your asymptotes. And so if you know your asymptotes, you can sort of determine, okay, this one's going to go this way, this one's going to go this way, and then these ones are going to start to go this way because this one's going to want to go this way, and this one's going to repel that one. So these ones are further away, so they're going to follow these two. But you can use MATLAB. And so what we're going to do here is basically, if we're to plot the root locus on MATLAB, what's going to happen is, give it a second to pull up. Okay. So what we're going to do here is if we create our live script, okay. So you first declare s as a variable, transfer function of s. And then what we're going to do here is RG is going to equal, copying it over, this is the open loop system, it's 1 divided by, and then s to the power 4 plus, and then 12 times s to the power 3, and then plus, and then we're going to have 64 times s to the power 2, and then plus 128 times s. And so then here, if we're going to then plot the root locus of this, you would do r locus and then of g, which is your system. And then when you run it, what you're going to find is once it performs it, you're going to see outputs s as transfer function, and then we made our open loop system. And then the root locus plot should pop up. Give it a second. Let me see. Let me just try doing it in live script, might be faster. There we go. And so then here's your root locus plot right here, and then it just shows what we got before. And so that's pretty much it. If you do that, you're able to define the root locus. An important part was, say if you need to find the poles of this system, like where the poles are actually located, there's a command in MATLAB, so you just use poles of G. And this, if you run it, it will tell you the location. Oops, sorry, pole of G. Be careful. Don't add the S. It will tell you where all the poles are located, just so you know, when you run that root locus plot. And so now that we did that, we're going to do another one where we need to, so switching back over. Here, we're going to choose a specific gain to achieve what we want. And then, so here, if we have our G of S is equal to S plus 1.5 all over S times S plus 1 times S plus 10. So we need to choose the gain K to achieve settling time. So choose gain K. So remember, when you choose a gain, that means that that's the block right before your G of S. So your open loop system's okay. And then here we have our G of S. And then it goes from here, unity feedback. So plus R of S. And then this is our output C of S. And so choose gain K so that the settling time is less than 4 seconds, less than or equal, and the percent overshoot is less than or equal to 10%. And so what we're going to see is for a settling time, remember, settling time is equal to 4 all over zeta omega n. So substituting that in here, we're going to have 4 all over zeta omega n is less than or equal to 4. And then remember, if we want percent overshoot less than or equal to 10%, using our table for zeta, we're going to see less than or equal to 10%. Zeta must be greater than or equal to 0.6. And so doing that, so we know that zeta must be greater than or equal to 0.6. And what we're going to find out is, remember, zeta is equal to cosine of theta. And so taking cosine inverse of 0.6, we get 53.3 degrees. So here we're going to have cosine inverse of basically 0.6 is going to be then less than or equal to our angle. And so then basically our angle, less than, greater than, so be less than, yeah, okay, wait, less than or equal to 53.13 degrees. Okay, so what here I did is we knew that our zeta, it has to be 0.6. So basically the cosine inverse, substituting cosine inverse for zeta, 0.6 must be greater than or equal to theta. And so then when you take cosine inverse, just rewriting it on the other side, you get less than or equal 53.13 degrees. Here, what we have for our zeta omega n, basically what we can determine, solve for zeta omega n. So if I swap this with this position, divide by 4, so 4 divided by 4, you're going to get 1's less than or equal zeta omega n. Just move this over to the other side, so greater than or equal 1, and then multiply by -1, you're going to get the following. And so plotting this, you remember, this would be at -1, because negative zeta omega n here on our real axis, this is equal negative zeta omega n is equal -1. And then our angle is less than or equal to 53 degrees. And so here is our angle. And then what we're going to notice is it has to be less than or equal -1. And so it has to be on this side, and it has to fall within the angle because it's less than or equal to 53.13 degrees. So it has to be in this section here. Okay, so that's pretty much it about how you would determine that, hey, we need our poles within this region. And so what we're going to see basically here is, can we specifically do that? And so what we're going to do is in MATLAB, we want to see, can we actually perform this? So I'm going to go to my live script. And so I'm going to just make a new script real quick. Actually, I'm going to work in the script this time. So remember, S is equal to the transfer function of S. And then we're going to have our G is equal to S plus 1. Oh, let me make this a little larger. S plus 1.5 divided by, and then what I have in my denominators, I have S, and then times S plus 1. And then times, and then this is going to be S plus 10. Okay, so now looking at this, what we have here, oh, I don't need all these. If we do our control, basically system designer, and then of G, what we're going to find is when we run this, let's see, looks like invalid, use parentheses. Oh, did we not use parentheses? Let's check. Control system designer, control system designer as time. Oh, we might have forgotten one. Let's look here. Okay, I'm gonna rerun that now. S plus y divided by s times. Oh, I forgot the multiplication in between. That's why. Run. Okay, and then it should pull up our control system designer. Should see it soon. Let's see. If not, then we'll go to here. Okay. So within our control system designer, it's going to plot the root locus on the left-hand side, and then it's going to plot the step response on the right-hand side. And so what we're basically going to do here is Bodhi editor. Oh, I think it's pulling up two windows because it was lagging. Let's close some of these tabs real quick. So I'll close this one. Oh, shut this real quick. Okay, let's rerun this now. And now since we cleared everything, we should see it pop up. Okay, so what we're going to be dealing with is we don't need the Bodhi editor for this. We're just looking at the root locus, and then we're going to look at the step response. So let's see if we can put these next to each other. Let's look at system. Okay, I'm just going to keep this one. There we go. Okay, so notice how we can get them two side by side. So our conditions here, we basically need to add a design requirement. And so our design requirement was that the settling time was less than 4 seconds. So hit OK here. And then we need to add a new parameter where the percent overshoot needs to be less than or equal to 10%. So that tells us basically where the location of our poles can be. And so here within our step response, basically here, we have to add the same design requirements. So our settling time is less than or equal to, it will give us an error if the rise time is less than is not less than the settling time. So I just made the rise time less than settling time and then 10%. And so now that we put those in, basically what we have to do is looking here, when we increase our gain, so I'm gonna pull this one here, and it looks like because at first it wasn't satisfied within these conditions, but when I started pulling the pole over here, notice that when I started pulling it, that it actually, because before it was over here, and it was not falling through, but when we started increasing here, our pole, it fell within the bounds of what our requirements were. And so looking specifically at our compensator here, which the compensator is basically your controller, your K. And so here, when our K was equal to 27.286, we were fine. Notice when you have a gain of 10, though, you satisfy, oh, look, it's not exactly within there, so you need to go just a little more. And so looking when we get to about here, 15, that's a good value for a controller in order to get the desired response. So it falls within our limits. And so that's using the control system designer. You have to make sure it's satisfied in the time domain. And so we saw, yes, these can be satisfied. Yes, when K equals about 15, it is satisfied. So that's what we noticed here. And then let's look at the next one, where the settling time needs to be less than or equal to 1 second, and the percent overshoot is less than or equal to 10%. And so we have the same angle because it's the same percent overshoot, so less than or equal to 53.13 degrees. And then our settling time, 4 divided by zeta omega n, needs to be less than or equal to 1. And so then our zeta omega n needs to be greater than or equal to 4. And then here, oh, give me a second real quick. So here what we need to do is our settling time. If we have to have it, our zeta omega n greater than or equal to 4, what we're going to have to do is looking now when you apply a negative, it flips the sign here to -4. And so graphing this now, doing the actual graph, at -4, this is your new condition where you have to be past. And so we still have the same angle, which is 53.13 degrees, so about here is our angle. And so now falling within between both those bounds, we're going to just be moved more over to the left-hand side. And so let's check in MATLAB if this is achievable. So going back to our MATLAB here, we're going to change. So you go to edit your design parameters. So our settling time, we have to now change to less than 1 second. So hit OK, so close. And then here we need to change the desired design requirements. So it's less than 1 second. Oh, we just go to design requirements now, and then let's just change it here. So instead of, so has to be, settling time is 1 second, so I hadn't made the rise time less than 1 second, or else it would give me an error. Percent overshoot is 10. And so here, what happens is, notice, if we try increasing the gain here, we're still not satisfying in order to stay within the white region, which is basically our bounds here. Notice that we are still not satisfied here. And so for any value K, if we move our poles along here, basically we notice that it's not going to satisfy the conditions here, basically. We can get close, but notice our percent overshoot is too much. Or notice when we're further away that we do not satisfy our conditions here. So that's the only issue, is that we can't satisfy, basically, with any value K, we can't get the parameters. So when you try changing your roots, you cannot satisfy this, no, as proved in MATLAB. So you cannot achieve these two design parameters here. Okay, now that we saw that, main thing is we are going to talk about delays. And so a delay is just like what it talks about, where it's a delay in time. And so what we're going to see is oftentimes delays are hard to implement. They make controlling the system a little more challenging. And so how they often represent delays in control systems is we have an RVS, our input, and then it goes through. And then we have a delay block, which is e to the negative ts. And then we have our system, G of S here. And then we have our output, C of S. So delays right here, when we try doing a delay, because when we work with the root locus, it requires a transfer function. And we need to represent e and negative ts as a polynomial. So root locus requires a transfer function, which is basically written in the form where you have a numerator polynomial of s and denominator polynomial of s. And so this is not in a numerator of s divided by denominator of s format. So what we do is we use the pod A approximation. So the pod A approximation basically puts this in the format so we get a numerator polynomial and a denominator polynomial. And so what we're going to see here is, say, for example, we have a delay. And so this is our delay here. And so we're going to have a delay of 1. So for an example, plot the root locus for no delay and a delay of 1 when g of s is equal to like 5 over s plus 3. And so if we have to implement the pod A approximation, basically says e to negative ts for a first order pod A approximation is equal to 1 minus t over 2 of s all over 1 plus t over 2 of s. Okay, so that's the first order pod A approximation. And so usually we use first order. A lot of times you can use second order. You can go up in order if you want. So if we have to plot the root locus for a delay and a delay of 1, what's going to happen is the root locus for open loop system, it's going to be the one without the delay is going to just equal g of s, which is going to be 5 all over s plus 3. But with the delay, what we're going to notice is, I'm going to call this LD of s, so with delay, it's going to be, here we're going to have our actual delay block, so the e to the negative st multiplied by our g of s here. And so this would be e negative st times our g of s. You're probably being like, hey, we can't express e negative st. And so when we plot this in MATLAB, what we're actually going to do is here, let's go to the MATLAB viewer. So we're going to close out this one real quick. And so here we're going to have, so our s is equal to a transfer function of, transfer function of s, transfer function of s, okay? And so we made s a transfer function of s. And so now what we're going to do here is we're going to have to write our specific code. So our L of S, so the L, sorry, for open loop system without the delay is just going to be 5 divided by S plus 3. And then if we're going to look at the system with delay, L with delay, so I'm going to call that LD is equal to, and then if we have to do this, it would be 5 divided by S plus 3. And then now we need to implement the delay block. So multiplied by, and then in MATLAB, what you do is use the keyword pod A. And then you do x to represent e times negative, and then it's t, which t is equal to 1 because we have a 1-second delay times s, and then the first order pod A approximation. And then after that, what you're going to do is you're going to implement here. Basically, we're going to plot the root locus of L, and then we're going to plot the root locus of L with the delay. And so we're going to plot both of those. And what we're going to see here basically is that we need to look at what it's going to be like. So we're going to compare the two specifically and see what the actual response will be for a root locus plot. And we're going to see about our gain margin. So I also want to see the margin of L. So we notice, hey, did the gain margin decrease or increase when we added a delay? And so let's just plot all this. And so notice that here's figure 1. So this was the first root locus we had here. And so looks like it gave us a Bodhi. Oh, because we said margin. So when you call margin, it plots actually the Bodhi plot here. And so let's look at, did that only plot the last one? It might have. So let's just first plot these first ones right here. So let me see if I can open that in the script. And then if we just run it, will require me to save it. So let me just go back here. Let me copy everything over. And then let me clear. And then let's just plot the root locus of the first one without the delay. So when we plot the root locus of the first one, notice that it's just a very simple system here. We had one pole, and so then it's just going to infinity. And then when we added the delay block in here, so just now plotting the root locus of with the delay, what we're going to see here is, if in this plot, it should pull up, is here. We go. So it introduced a pole and 0 because of the pod A approximation. And what we're going to see here is that we have to be a little more careful because now your system can go unstable. Notice here it crosses into the right-hand plane, where before it didn't cross into the right-hand plane. So the pod A approximation does make your system unstable, so you have to be careful about that when you use it. So that's the only thing. Be careful when you add a delay because it decreases your gain margin. Notice in the previous one on we're going to plot the margin actually both. So if I just plot the margin of L, what you're going to see is your gain margin. We're going to compare that to when we added the delay. So should pop up right here. So our gain margin's infinity. So we can add as much gain as we want. But when we did the margin with the delay, L with the delay, what we saw was actually that the margin, now the gain margin went down. It's no longer infinity. It's an actual finite value. So when you add a delay, you decrease how much gain you can implement in your system. So just notice that delays make your system, they can make it unstable. So you have to be careful. And so now that we saw that, basically, now we're going to look into the next one, which focuses on design using the root locus. And so this is going to be important, seeing how we can actually design either lead or lag controllers in order to get the output that we desire. And so let's go over to that. And so the design using the root locus method is we're going to use a compensator. And so here